Hi everyone, hope you've been keeping well. Know the past few months have been hard for many people, but surely the world will return to normality, a better normality, very soon. So let's continue our discussion of the mathematical modeling of the infectious diseases. We have covered the basics of deterministic and stochastic models, and we still need to cover network type models and also the calibration implementation of these models. But let's try to understand the very important concept of basic reproduction number that drives a lot of policy decisions, and understanding this concept will also ease the transition to network type models. We will then look to cover estimation of this parameter from actual data in a subsequent video. Remember, the reproduction number refers to the R0 we saw in the deterministic video, though the concept is not tied to any model. It rather depends on the transmission dynamics of the disease. And one encounters this same very concept in many fields: nuclear chain reactions, extinction of species. So the reproduction number determines whether a nuclear chain reaction will lead to explosion or humans will go extinct. The description of R0 is very simple. You have the population consisting of just susceptibles. You introduce one infective and count how many people does it directly infect over the course of its infection. Why would such a simple thing carry so much information? So this is what we're gonna find out. By looking at the definition, you can tell that the concept is trying to measure the growth potential, and a good measure of the growth potential will surely answer a lot of questions, such as whether the introduction of the infective will lead to epidemic, and how much effort will be required to contain the spread. And you're right, this is what R0 does. But then why not use some other concept, say the compounding or exponential growth rate?
In the branching processes, this is called Malthusian parameter. The parameter is named after Thomas Malthus, a British cleric and scholar, who essentially said that left to its own devices, population will grow exponentially.
He was more concerned about catastrophe than growth, to be honest. Now, this exponential growth has certainly been a strong contender, but then we know that the transmission processes of different diseases could be quite different. For example, malaria doesn't spread from person to person but through mosquitoes. A mosquito biting infected human becomes infected, and then it can infect another human, and the cycle repeats. Or one can have heterogeneous population where different people have different infectivity and susceptibility. The reason R0 wins is because it generalizes across many such situations, retaining the same very description, and mathematically is also very elegant. It has its limitations, but it is in advantageous position compared to the alternatives. So for people who still remember algebra, R0 for most cases amount to the same thing as the dominant eigenvalue of a matrix, the matrix being the next generation matrix, which you can view as providing the link between the two consecutive generations of infectives. We shall see the details shortly. By the way, we will be mentioning some concepts from algebra, some of which will appear abstract at places, but it will hopefully come together in the end, or at least the story will flow. So if you don't follow one or two technical details, I think you'll be alright. You need some abstract stuff in between because the aim is to generalize the concept, to see the forest for the trees, and the advantage then is we will be able to analyze many more complex transmission mechanism using some simple basic algebra. Now, as an aside, recall that when solving system of differential equations, one can gain a lot of insights about the solutions of these systems through qualitative analysis. One such analysis tool is the equilibrium analysis, or the stability analysis around the equilibrium. So one linearizes the system around the equilibrium, and this linearization reveals a lot about the underlying functions. Here you can see the word virgin, and the definition of R0 is a clue that we are linearizing the problem, because we know that as the number of infectives increases, the number of susceptibles declines, so it is a nonlinear problem. But by assuming virgin population, we are essentially saying that the infectives encounter constant conditions, which is the same thing as a linearization around the equilibrium, but the equilibrium definition is slightly different than what you would have seen in the differential equation course. Here, it is disease-free equilibrium, which is the same thing as a virgin population, free of any infectives. So as you would have anticipated, there are two ways to approach the R0, via linear operator and algebra, or via disease-free equilibrium analysis. We will take the algebra route in this video and then cover the equilibrium approach in a separate video. There is also another approach in the form of Lyapunov analysis, which is like equilibrium analysis. Involves a mixture of algebra and differential equation, but we will leave it as a topic for self-study. Let's dive in. Let's consider some time scale from 0 to t. So we have our case 0, and infective is introduced. It takes a while for it to infect another individual. A moment later, it infects another individual, and then another. And then let's say it itself is not infective anymore, but it has done its bit for the infectives to grow. The second of its infectives is the first to reproduce, but luckily only one. The first one infects 2 individuals, and the last one turned out to be a super spreader. Let's see a couple of more branches. Now this branching process view provides a very natural representation of the reproduction process, but the data usually made available is a daily count of cases as opposed to the generation view. What it means is the data is reported by slicing the time into intervals, say daily, and the total cases in each interval are reported as time series. While this is certainly easy to compile and report, but you can see mathematically the generation view is easier to analyze. For example, if one were to incorporate the Markovian assumption, then in the generation view it's quite natural, but making the time series view Markovian would be quite messy. Anyways, once we have taken a few more steps, we shall be able to infer the time series view from the generation view. Let's develop this generation view then. An important tool in statistical analysis is the cohort analysis. So here we form a cohort based on the onset of the infection. We just change the view to landscape so that we can accommodate many infectives in parallel based on the onset of infection. An advantage is now we can generate the behavior of a typical infective over the natural course of its infectivity. Essentially, how and when does an infective infects other people over the natural course of its infectivity. We can summarize this information in a cohort table showing the average cumulative number of infectives over time. Let's say time is in days, so we are tracking 6 infectives here. In reality, one will have a much larger sample, but it's the thinking we are after. So in the first day since the infections, none of their infectives infects anyone. We do need sensible people like them. And then on day 2, they infect 4 people. Then on the third day, they infect another 6 people. So the cumulative number of infectives caused by the cohort of 6 infective becomes 10. On the 4th day, they infect a further 2 people, increasing the cumulative sum by 2. And then they infect another 2 on the final day of their infectivity. So in total, there are 14 infectives produced by the 6 infectives over the course of their infectivity. We are after an average infective, so we divide the cumulative sum by 6 to get the behavior of a typical infective. And we see an average infective produces 2.3 infectives, and this 2.3 is our R0. And don't forget, this cohort analysis is a way to summarize the generation tree or a branching process. Now this branching process, as you can easily see, can be applied to many processes. For example, nuclear chain reaction involves similar dynamics, but here you will have, say, neutron release and a fission producing fission in another nucleus, releasing more neutrons and so on. The equivalent to R0 is called the neutron multiplication factor, and usually represented by k, and similar thresholds apply. So if the multiplication factor is less than 1, the chain will die out. For k equal to 1, the chain will be self-sustaining as the number of neutrons will remain constant, which is what you want for nuclear power plant. And if k is greater than 1, then the number of reactions will be increasing exponentially and you could have the nuclear explosion. The moral of the story is if you have a secret, don't share it with greater than or equal to one person, which means no one. Definitely never let more than one person in on the secret unless you want the whole world to know. Nuclear chain reactions are relatively a recent thing. Branching type approaches have been used in modeling population dynamics much before the chain reactions. There are two parallel developments, one concerning the male offspring of males, particularly motivated by the observation that many surnames disappear after some time, meaning they don't produce enough offspring. Remember, in those days only the rich and famous used to have family names, so it was an important issue. Here is one such problem posted by Colson, though a similar thing has appeared before then. So we have a group of n man with different surnames. In each generation, the probability that a man will have no male children is A0, probability of one child is 1, and so on. And the question then is to determine the probability of extinction after R generations, R being a generic number, and the size distribution of the surviving surnames. The problem was solved, but a key mistake in algebra meant the wrong solution was accepted for a very long time. Life can be tough. The second parallel development focused on mothers and daughters because of the fact that the human population growth depends on female, and hence the extinction of the human race is down to how many female offspring a female produces. This data is of interest to many public agencies, so the fertility data is compiled on a regular basis by the statistic offices in many countries. For us, what it means is we can source some real data that we can connect with and then use this data to introduce the integrals, so everything will be grounded in reality. Our UK Office for National Statistics compiles and publishes a lot of statistics on female fertility, so let's source one such series. As in the analysis of epidemics, it's common to report the data by cohort of people, where the cohort is defined based on the time of birth. So here we are tracking the fertility of the cohort of all women born in 1973. So you can see from the horizontal axis that the fertility starts at around 16. The most of the increase happens at around 30. That's where the curve is steeper. If you plot the data for more recent cohorts, you would see the curve shifting to the right. This is because, as any newspaper would tell you, people are delaying having children. Maybe they have more things to do now. Reckon video games are to blame. By the way, we are interested in daughters, but here the birth includes both boys and girls, but worry not, we can just assume that 50% of the births will be females. So what is this telling you about the reproduction number then? It's less than 1. It means extinction is the destiny. So you can see the cohort view arises quite naturally. However, one can do better. You can see that not all of the women born in 1973 would have lived to the age of 30, so the birth rates at different times are not really like for like. It's more revealing to split this data into two parts, survival rate and fertility conditional on survival. Sounds probabilistic, but actually ONS compiles such data. Survival should not be too hard. You can again select a cohort of women born in a given year and track how many of them are alive. This is your survival function, easy peasy. Now for the conditional fertility rate, you can count the number of births at a given time by the age of the mother and then divide by the currently alive females and the respective age group. Very little to do there. We are interested in females only, so assume we can divide the births by 2 to get the number of girls, and let's remove the boys from the charts. And now you can easily see that by combining the two curves, you can easily reproduce the cumulative birth by cohort graph. Let's go through the steps very slowly so that we can introduce some mathematical symbols. Let Bt represents the number of female born at time t, and we know this graph represents the number of female births by age of the mother. We can see the first data point came from woman aged 15, so it would be down to the women who were born 15 years ago, which is t minus 15. The second data point would be down to women born 16 years ago, and so on. You can see the peak occurs around the age 30, and the last entry represents all ages over 45. Now we can treat the age as a variable and represent it by A. Now this represents the number of female born A years ago, assuming we are at time t. Now not all of the females born A years ago would have survived, so let's represent the survival rate by Q. So Q represents the proportion of women who live to an age of at least A. The product of these two then represents the total number of women who were born A years ago and are still alive, or to cut a long story short, just the current number of female of age A. And if you multiply this by the age-specific fertility rate, you get their contribution to the current births. Now you can see the product of the survival probability and the conditional birth rate gives you the expected number of births to a female born A years ago. So it is kind of maternity schedule. And we can combine the two terms and call it M. Remember the first chart we saw? So this M represents the rate of increase in the cumulative births at each age A. And if you're happy to treat this as a continuous variable, then M represents the derivative of the graph, which is just the rate of change with age. And then you can say that R0 is the integral of M. So R0 is just the cumulative number of births, right? And if you then sum across ages, keeping t constant, you get the total number of births as at time t. And if you're happy to treat A as a continuous variable, then summation becomes integral. Now this is a beautiful equation.
What you see is really a special form of the renewal equation.
And one can do a lot of beautiful things with it, but we are interested in applying this to another type of reproduction process, the reproduction of infectives. So let's switch the context. Now the infectives don't take 16 years to produce another infective. For the virus we are interested in these days, it is a matter of days. By the way, have you heard of the allometry in biology? These are like the equivalent of Newton's laws but more qualitative. One of them says that the maturation time is proportional to the weight or size of the organism. Coronavirus is not an organism, but if you apply this allometry using human size and maturation time as benchmark, you would get maturation time of about 50 to 100 days, which is not too far from 5 days in the scheme of things. Now the equivalent of birth is infection, so let's replace B by I, and we also reduce the age scale from years to days, and also the maturation time from 15 years to a couple of days. And let's also replace the age by time since infection, which sounds better with tau, and the maternity schedule becomes infectivity schedule, which is usually represented by capital A. Also remember, an infective can interact with all of the susceptibles, so the number of infections it can produce will be proportional to S, where S represents the number of susceptibles, so we multiply by S. The infectivity curve will also take slightly different shape. The peak will be towards the left, with infected person generally more infective around the time of the onset of the symptoms. Now if you sum across tau, we get the total number of new infectives at time t. And if we assume tau is continuous, then as before, the summation becomes integral.
And we now have the same renewal equation, but for the infectives.
Now this is nonlinear equation because S, the number of susceptibles, will change with I. But if we assume that the number of susceptibles doesn't change, then the equation becomes linear. It's linear because the function I appears in linear form on both sides. If we had, say, square of I or some other nonlinear function of I, then it would have been nonlinear. And the equation is homogeneous because we don't have a source term. Linear homogeneous equations, as you would know, are easy to handle. The solution of such equations usually takes this form. You see the same very form in the solution of ODEs. So let's substitute for I on both sides. Notice the integral is with respect to tau, so we can take the term with the exponential of RT outside the integral, which cancels the same term on the left hand side, and I0 cancel as well because it is a constant.
And this is the famous Euler-Lotka characteristic equation.
Now compare this equation to the expression for R0. We have kinda discounting factor, and what this discounting factor does is make R0 equal to 1. This is the exponential growth that Malthus was talking about and goes by the name Malthusian parameter in the branching process literature. You can easily see the comparison between the Malthusian parameter and our R0. If R is positive, it means the discounting factor is needed to make the R0 equal to 1, which means R0 must be greater than 1. And if R is less than 0, then we know R0 must be less than 1 because the exponential factor with positive exponent is needed to make the integral scale to 1. And obviously when R equals 0, R0 equals 1. Whilst the sign of R tells us about what region R0 will fall into, establishing relationship between magnitudes is tricky, though one can employ this relationship to estimate the R0 from the exponential growth rate usually seen in the daily cases in the early stages of the epidemic. Now, if you think of the integral as a linear operator, then this parameter R is chosen in such a way as to make the eigenvalue of the operator equal to 1. The connection between the linear operator and the eigenvalue might not be obvious here, but it will become more obvious when we complicate the dynamics a bit. Then you would be able to see the matrices in vectors and the eigenvalues in eigenvectors associated with them. And if you don't buy the linear homogeneous story, then you can come up with the same result by staring at the equation for a few moments. Let's do it together. Let's say we don't know the answer is 1, so let's replace 1 by a function of R. This is because the right hand side got to be a function of R only, as the other variable tau is integrated out. Now let's try to plot the function f as a function of R. We don't have the exact function to draw, but we can infer its properties quite easily. We know S0 and A are positive. Assume R can be any real number from minus infinity to plus infinity. As R goes to minus infinity, the exponential term will go to infinity, and as R goes to plus infinity, the exponential term will make the expression go to 0. So we can see the function will take a large value on the left hand side and a small value on the right hand side. So we got 2 points. Now let's explore the rate of change of this function so that we can connect the 2 points. Take the first derivative with respect to R, which is quite easy because R appears in only one place, and this must be negative because all the terms are positive, so the negative sign in the front persists. So the function is decreasing, but is it decreasing at an increasing rate or at a decreasing rate? To find out, take the second derivative, which turns out to be positive. So the function is decreasing, but the second derivative is positive, meaning the first derivative becomes less negative as we move to the right. So the function will take this form. Now the function is monotonically decreasing, so it can equal 1 at just one value of R, and we conclude there's one real root R, and there you go. Now we could have inferred a lot of information about the variables of interest appearing in these equations without doing much had we used some theorems from linear algebra, but using linear algebra in this simple homogeneous case is so simple as to kill the fun, so let's introduce more variations. This shall make the models more sophisticated and more practical as a result, and we will be able to analyze a large variety of infectious diseases. The price is not too steep, so no brainer. In the homogeneous case, every infective had the same infectivity, or shall we say infectivity kernel to be more precise. So the infectivity only varied by tau, which is the time since infection. That's a very strong assumption, right? So let's get a bit more realistic and assume that the individuals have different infectivity and susceptibilities depending on some traits or behavioral characteristics. So the infectivity kernel gets two more parameters. These Greek symbols xi and eta represent traits or characteristics of the individuals. We represent the collection of traits by omega. These could be static traits that don't change with time, or dynamic behavioral traits that do change over time. All you need to know is that there is a set of traits, and people with different traits have different risk of contracting and transmitting the disease. And we assume that individuals who share the same traits are homogeneous. So there is not a single homogeneous class of susceptibles anymore, and we have divided the population into classes based on the traits, and our susceptibles will now be a function of traits, and so will be the infectives. They will essentially be distributed into the subclasses. This might seem abstract, so let's enumerate a few examples. If the presence of a health condition is the key driver of the heterogeneity, then omega will just consist of two traits, people with the health condition and others. If age is the key driver, then omega could be the set of age groups, or age could be a continuous variable if we think more granularity is appropriate. If both age and health conditions are the drivers of heterogeneity, then omega would be the cross tabulation. One can go as general as one like. Sky is the limit. Of course, the set of traits one chooses will be driven by the dynamics of the disease being modeled. So these could be the characteristics that differentiate the contact rate, infectivity rate, and recovery rates, etc. Say we decided that gender and age are the key driver of the heterogeneity, then S and I will be the distribution of population by gender and age. Of course, here we are talking about generation view, so these distributions will change from generation to generation, and this is the main modeling question. Now back to our infectivity function or infectivity kernel. It represents the infectivity of an individual who was infected tau times ago while having trait eta towards the susceptibles who has the trait xi. So the infectives are identified based on the class that they fall into at the time they got infected, and for susceptibles it's the current class that matters. So the infectivity rate of a 25-year-old on the 5th day of his infection towards an 85-year-old will be represented as follows. Now you can easily write the equivalent of the equations on the right hand side. Let's start with the first. We just have to put the eta and xi in the right places. Notice I on the left hand side as xi as parameter, whereas the one on the right hand side inside the integral as eta. This is because an infective who got infected tau times ago while having trait eta infects susceptibles with trait xi. So the new infective has trait xi at the time of infection. Now for the second, we just need to linearize the previous equation, so we just replace t by 0 inside the function s, and I put 0 in the subscript as well so as to make it easy to read. So we are fixing the number of susceptibles available for infection. For the R0, if we want to copy the right hand side, we will just need to add another integral. This is to sum across the traits. Previously, we could just use the aggregate number because everything was homogeneous. But this is not going to work. Reason being, this will give us the R0 using only the infectives with trait eta. But how about the infectives with traits other than eta? But then you might ask, why not calculate R0 for each homogeneous group of traits and then average across groups? This could surely be used as an approximation for R0, but it ignores the interaction between the groups, so likely to understate the true figure. We need an elegant averaging method. It is easy. Take the current distribution of the infectives and move straight to the operator form. So this phi represents the current distribution of infectives by trait, and you know the expression on the left hand side is just abbreviation for operator k applied to the function phi, and this will produce a function of xi. Lambda is the Malthusian parameter. Essentially, phi is the current distribution of infectives by trait, and applying the operator to it gives us the distribution of the infectives in the next generation. Remember, mother, daughters, same thing but in abstract form. We shall consider concrete examples in a bit. Comparing this operator to the function f on the right hand side, we just replaced a typical infective by the distribution of infectives, and we need to add another integral with respect to eta so that we can sum across the traits that define the distribution of infectives. Now this is again a homogeneous equation, but it is a function of two parameters now, time and trait. So we know more now from our model, say number of elderly infectives or number of male infectives depending on what traits we have chosen to model. So previously we argued the solution will take this form. Now it will take similar form, but the initial condition now becomes a vector, which is the eigenvector or eigenfunction of the operator. We shall see in a bit its finite dimensional example, which shall bring it in the more familiar territory of eigenvalues and eigenvectors of matrices, but think of this as the slightly more abstract version of the same things. Remember the eigenvalue equation? So here we can write the same relationship, just the matrix A gets replaced by the operator, which is easy to relate to if you remember that multiplication by matrix is really a linear transformation. Also recall that one can use the eigenvector as the basis and write a vector as a linear combination of the eigenvectors. So the C's are constants that are chosen so that the identity holds. Now what we would like to know is that if we take the current distribution of infectives, what will happen to this distribution over many generations? Very easy thing to do. You take the current distribution, apply the operator to it, and you will get the distribution of the next generation of infectives. Apply k again, and you get the next generation. So to get the distribution after n generations, you just multiply it by k n times. Then let n goes to infinity and you will have the limiting distribution. But we are interested in R0, which measure the growth factor from one generation to the next. Remember, it's the number of infectives produced by one infective. But then this number could vary by infective because each infective is special now because of the heterogeneity we introduced. The fix is again easy. We can just take an average per generation. Here, as you can appreciate, geometric average seems more appropriate. So we have the mathematical definition of R0 for heterogeneous structure, which is super cool, but is it easy to calculate? Multiplying matrices n times could take quite a few afternoons, but worry not, eigenvalues and eigenvectors make such calculations quite easy.
And it really is a piece of cake, if you know your Perron-Frobenius theorem.
To get the basic idea, assume you have positive matrix. Positive means you have a square n by n matrix, each element of which is positive. It won't be too strange if someone were to ask what does the positivity of the matrix says about the eigenvalues in eigenvectors. Should we expect positive eigenvalues in positive eigenvectors? Perron theorem answered the question by saying that the largest of the eigenvalues is positive, and the eigenvector, both left and right, associated with these eigenvalues are also positive. The largest eigenvalue is what matters in the long run, so we can ignore the rest as we shall see very shortly. Now, Perron proved this for a positive matrix, but since a positive matrix is just a special case of irreducible non-negative matrix, then Frobenius gives similar results for these matrices. I have copied these from the Theory of Matrices book. By the way, non-negative means the entries could be 0, An irreducible matrix is easy to explain with a little bit of calculation. Let's say this matrix represents the transition between two states. We can see two of the entries are 0, meaning there is no transition from state 1 to itself, or from state 2 to itself in one step, or in one generation in our case. Now, if we calculate the two generations flow by multiplying the matrix by itself, we see that the two entries that were 0 are no longer 0, meaning there's flow from state 1 to itself over the course of two generations. And when each of the entry becomes positive for some power of b, the matrix is called irreducible. We shall see an example of disease transmission whose generation matrix takes this form later on. Now the equation we are facing is essentially a positive operator, and there's a version of the theorem for such operators. Why is it positive, by the way? Well, all the functions we have are positive. S is positive, distribution function phi is positive, a is positive, and exponential function is positive. So the overall integral will be positive. So the theorem tells us that the largest eigenvalue will be positive and will have positive eigenvectors. This largest eigenvalue goes by several names: dominant eigenvalue, Perron-Root, spectral radius. Quite impressive list of technical sounding names one can impress with. Now, to see how could this help simplify the calculation, let's write k times phi, which is the operator k applied to the distribution function phi in terms of the eigenvectors of k. So we just wrote phi as a linear combination of the eigenvectors. We can take k inside the summation. So previously we were adding the scalar multiples of the eigenvector and then multiplying the resulting vector by k. Now we are multiplying each eigenvector by k first and then calculating the linear combination. Just the order of calculation has changed. Now by the eigenvalue equation, we can replace k times psi by lambda times psi. And if you multiply by k again, and then replace k times psi by lambda times psi as per the eigenvalue equation, you can see it's equivalent to just squaring the lambda. So we can generalize this to n. So 2 will become n, and which is exactly what we need. Now let's say the dominant eigenvalue is the dth eigenvalue. So we multiply and divide it by this eigenvalue. Now split the summation term by splitting out the dominant eigenvalue term. Now what happens when you let n goes to infinity? As lambda d is bigger than the other eigenvalues, this term becomes smaller as we increase n. So the summation goes to 0. And hence just retaining the leading term will provide a good approximation for large n, and the approximation will be better the larger the n. So what is this dominant eigenvalue? It really is our R0. The eigenvector is capturing how the infectives will be distributed by traits. Note, this is not the initial distribution of infectives, but rather the stable state of the distribution of infectives. The initial distribution affects the fixed scaling factor C, so you can view C as the contribution of the initial condition. Remember, C's were the weights assigned to the different eigenvectors so that their weighted sum equals the initial distribution. And now we are left with only one of those coefficients, the one associated with the dominant eigenvalue. As the eigenvector is fixed, the growth in infective from generation to generation is just down to R0. So in summary then, the eigenvector associated with the dominant eigenvalue is the distribution of infectives, and in each subsequent generation, the total number of infectives grows by the factor R0. So R0 is the average growth rate from one generation to the next. Now you can ask, what happens when R0 is less than 1? What happens when it is equal to 1? And what happens when it is greater than 1? And you can see R0 here as the same interpretation as in the simple case. Don't let the integral and continuous variables come in the way of the analogy with the simple case or with the algebraic interpretation. one can easily construct a discrete version of the heterogeneous case. So previously we defined A as the infectivity towards the susceptible of type Xi of an infective who got infected tau times ago when it had trait eta. For discrete version, one replaces continuous trait variables with indices. So the discrete version can be written as follows. I and j represent the traits of the individuals. These could be, for example, indices for different age groups or gender or health status. So it represents the infectivity of individual of type J to an individual of type I. Note this is read from right to left, so it represents infectivity from infective J to susceptible I. Tau represents the time since infection, so it helps us capture the pattern and infectivity over the course of infection. As we are interested in the generation view, we can aggregate the infectivity over the infectious period, and this now represents the total number of susceptibles of type I that an infective of type J will infect over its entire infectious period. Assume in total there are m types of individuals, so these could be m age groups, for example. Then the m times m matrix will represent the infectivity of the different types to each other. So the first column represents how many infectives of the m different types will an infective of type 1 produce. The second column then represents how many infectives of the m different types an infective of type 2 will produce, and so on. Now, if you can get the distribution of the infectives as of generation n, so this vector represents the number of infectives of the m types in generation n. Phi 1 represents the number of infectives of type 1. Phi 2 represents the number of infectives of type 2, and so on. Then using matrix A is easy to determine the distribution of the infectives in the next generation. You just multiply A and phi to get the next generation distribution of the infectives. The matrix is then rightfully called the next generation matrix. Just to check the arithmetics is right, you can see first row of A times the column vector will give the infectives of type 1 in the next generation. You can see it's correct because multiplying infectives of various types by their infectivity to type 1 will give the infectives of type 1. Now if we have the initial generation, this generation 0 distribution, and we multiply it by A, we will get the distribution of generation 1. If we multiply the generation 1 distribution by A, we get the distribution of generation 2. We can write the generation 1 distributions in terms of generation 0 distribution. So we get A squared, meaning multiplying generation 0 distribution by A squared gives us the second generation distribution. And then we can say that multiplying generation 0 distribution of infectives by A to the power n will give us the distribution of the infectives in the nth generation. And now it's easy to see how the eigenvalue and eigenvectors come about. The continuous variables integral version that we have been playing with is just a slightly more abstract version of this same very concept. And by the way, heard of the page rank algorithm? It's based on the same idea. Eigenvector associated with the dominant eigenvalue is the ranking of the pages. So everything we are seeing here is used on a daily basis, but by Google. And for another use, one can also use this theorem to rank the football teams in a league, which might be a way to settle the title because the games have been suspended mid-seasons due to the lockdown, so we don't have a winner. But the eigenvector associated with the dominant eigenvalue can provide the answer. So Perron-Frobenius is the answer to a lot of questions, including our R0. Let's see the rewards of our generalization now by considering examples of various transmission processes. Let's start with malaria, which is a type of vector host disease, mosquitoes and human respectively. Similar structure would hold for transmission of the STD in simplistic settings in which we only consider transmission between males and females. So in each generation n, we will have the number of infected mosquitoes and the number of infected humans. So the infectives is a two-dimensional vector. The next generation matrix would be the off-diagonal. The diagonal entries are 0 because the assumption is that the disease doesn't spread from human to human or from mosquito to mosquito. The spread happens via the interaction between the infected individuals of one type and the healthy individuals of the other type. So K12 represents the number of susceptibles of type 1 who will get infected by an infective of type 2 over the course of its infection. Type 1 could be mosquito, type 2 could be human, or for STD in the heterosexual case, type 1 could represent males and type 2 could stand for females. Now to determine R0, we just need to calculate the eigenvalue of a 2 by 2 matrix. First, could you verify that this matrix is irreducible so that we can apply Perron-Frobenius? We know the off-diagonal entries are positive, so we need to check if the diagonal entries, which are 0, do turn positive for some power of k. If you multiply the matrix by itself once, you get diagonal matrix, so you can see the matrix does imply link between all states and hence is irreducible, so Perron-Frobenius works. But first, let's see whether this generation matrix works by checking whether the next generation it produces makes sense. Substitute for k in phi n and then multiply. So you can see first row, which is the number of infectives of type 1 in the next generation, is equal to the number of infectives of the other type times k12, and same goes for the second row. So the human infectives in this generation are produced by the infected mosquitoes of the previous generation, and infective mosquitoes are the ones who fed on infected humans of the previous generation. So let's quickly calculate the eigenvalue. Remember from the first year algebra, to calculate eigenvalue of a matrix K, you just subtract a matrix which has the symbol for eigenvalues in the diagonal and 0 everywhere else, and then set its determinant equal to 0. So for our matrix K, it becomes, now determinant of a 2 by 2 matrix is just the difference of the product of the cross terms, and then you isolate lambda on one side and you have eigenvalues. We are interested in the positive one, so you can see the reproduction number is the average over 2 generations, which makes sense because the transmission cycle is 2 generations, human to mosquitoes and back to human. Can you also calculate the eigenvector, please, and see how the stable distribution of the infectives will look like? You can assume the initial distribution has just one infected mosquito and 0 infected human, or the other way around. Now let's consider the simple SEIR model. It's a piece of cake by comparison. In the deterministic case, we saw that the rate of change of the 3 compartments can be defined in terms of the differential equations. These are the same equations, by the way. The prime denotes the derivative with respect to t. So here, there's only one type of infectives. This is because of homogeneity assumption. So our generation vector consists of just one row. It's essentially a scalar, but we write it in a vector form so as to retain the similarity of method with the other cases. The next generation matrix or multiplication factor here is easy to derive. We know an infective leaves the infective compartment at the rate of gamma per unit time, so it stays infective for 1 over gamma period of time. Easy way to prove this is to see that this ODE amounts to the assumption that the infectious period is exponentially distributed with parameter gamma, and you know the mean of the exponential distribution is just 1 divided by gamma, and then it in fact susceptible at the rate beta times s per unit time. So the generation matrix is rather very simple. Notice we use R-nought, so we are assuming that the susceptible population doesn't change. This is the linearization assumption that we were discussing at the start. And you know the eigenvalue of this one-dimensional matrix is just the single entry. So we have our definition of R0, which is the same result we saw in the mathematical modeling video, which is reassuring. Now you might be wondering, how does it compare to the integral representation? Remember earlier in the simple case, we had R0 as follows, which is essentially the total number of infectives produced by one infective over its entire period of infection and an entirely susceptible population. The simple SEIR model amounts to assuming that the A takes this form. You see the exponential distribution and the constant per unit infectivity rate, beta. Let's see if it gives the same result. Let's substitute this expression for A and the integral equation, and then evaluate the integral. Exponential of minus infinity is 0, and the exponential of 0 is 1, so we get the same result. So we can see that the different representations amount to the same thing. This was a simple case, the answer to which we already knew, but the concepts we have now at our disposal will help us analyze more complex models with ease. Let's discuss a slightly more realistic example of the SEIR model. Say we have two types of individuals. In the COVID-19 case, the two types might be young and old, or people with underlying health conditions. You can use more groups instead of two. The explanation would be similar and the mathematics the same, but we have little space on the screen, so we stick to two groups. We also include natural births and deaths, but we assume they cancel each other, so the total population is constant. As you expected, there will be two equations for susceptibles, one for each type. Mu is the birth and death rate, so a proportion of birth happens in the S1 compartment and the remaining in S2. Notice we are assuming that all of the births happen in the susceptibles. That's why we have N here, the total population, and the natural deaths happen at the same rate in each compartment, so that's why the deaths are proportional to S1 and S2 here, and we will have similar term in the other compartments as we shall see shortly. Now we have two betas. B11 times S1 represents the number of type 1 susceptibles infected by the type 1 infective, and B12 times S1 represents the number of type 1 susceptibles who got infected by the type 2 infectives, and a similar interpretation applies to the second equation. Now we assume there is an exposed stage, so the susceptibles flow into their respective exposed compartments when they get infected. So the first two terms are just the inflows from the susceptible compartments. V1 and V2 represent the flows to the infectives compartments, and mu represents the per unit death rate due to natural causes as before. And then the infectives equation will just be the inflows from the exposed compartments minus the outflows to the recovery compartments, and the last due to natural deaths. Gamma 1 and gamma 2 are the outflows to the recovery compartments. We will have two equations for the recoveries, as we already know how they will look like. We don't write them here. Now let's translate this into our distribution vector and the next generation matrix. There are two types of infectives, so we can represent the number of infectives in generation n by a two-dimensional vector. The generation matrix would be 2 by 2, which we write and then explain. By recalling the interpretation of the next generation matrix, we see, for example, that the first entry in the first row really represents the number of susceptibles of type 1 infected by the infectives of the same type. In analogy with the previous case, we know a typical infective will spend 1 divided by gamma plus mu time in the infectious compartment, and during this time, they lead to sending B11 times S1 susceptibles of type 1 per unit time to the exposed compartment. They then spend 1 divided by V1 plus mu time in the exposed compartment, producing infections at the rate V1 per unit time. So the first entry is the total number of susceptibles of type 1 that a typical infective of type 1 produces over the infectious period, and you get the other entries by applying this reasoning to the flows between the various types. One can narrate the story around the construction of the entries in several alternative ways, And then for R0, you're just calculating the eigenvalue of a 2 by 2 matrix as in the previous case. This process of writing the generation matrix is quite simple, but in a subsequent video when we discuss the disease-free equilibrium approach to the derivation of R0, we shall see a more programmatic way of producing this matrix, so constructing the matrix is gonna get easier from now. Now exercise time. Assume an SEIR model in which the exposed class, infectives who haven't developed the symptoms yet, can also infect other people, but maybe not at the same rate. So we change the susceptible equation to factor this in, where epsilon is there to allow for the possibility that the infectivity in the exposed stage may be different. We know how to write the other equation, so the problem is similar to the previous examples we discussed. Now, could you have a go at the next generation matrix for this problem, please? I will leave you to it and look forward to seeing you in the next video.